Thank you very much for that very positive introduction of me, and thank you for inviting me to speak here. I'm very happy to come and join you for this hour. So what I'm going to do today is a little different from what I normally do. As she just mentioned, normally I do very quantitative things, and I put a lot of equations and math on the board. Today, what I want to talk about is something a little bit higher level, how we situate that kind of work in academia and in the world, and how we make it happen at this junction in history when data science, big data, all of these things are very much of the moment. So at my job at OSU, half of my salary comes from the translational data analytics unit, which requires me to think about this set of issues in terms of what I do and choose to do and how I mentor my students. But I've never had an opportunity to run these ideas by a big group of people like you. So this is an experiment, and partly what I want to do is get your feedback on how I'm framing this kind of work and what I do. So the title is Multi-disciplinary Data Science to Improve Global Health, Verbal Autopsy. It's one of the main project that I work on at the moment. So data science for social good is something that we hear a lot, and universities like to make statements about how they support it. Most universities, big ones, have an e-science institute or a translational data analytics institute or something similar to that. And this is typically one of the objectives that the institute has to support this kind of work. Except I see very few specifics about what it actually is. So I tried to think through what these would be and provide some definitions, and I'm eager to get your feedback if you think there are different or more things that should be here. So for social, I think it relates to something to do with the welfare of people, individuals, and groups of people. Good, there has to be an improvement in something having to do with welfare, and it has to be specific. I see a lot of talk around this set of issues that is very non-specific. So I think we need to be specific about what we're trying to improve and what that improvement actually is. And then I think in order to do something good in the world, you need to actually be able to do it in a sustained way. You can't do something today and decide that you're going to do something different tomorrow and not have a plan for sustaining whatever that is. Data science, I think we all have some inkling about what data science is. To me, it means a combination of thinking about data themselves, how the data are generated, how they're curated and transformed into a situation where we can make sense of them, and then all of the analytical techniques that we use to generate new knowledge from data. So it's both data and analytical approaches. Research, I think, given that we're academics, is an important part of this data science for social good. People do it in industry and other places without maybe the research component, but here I think we need to incorporate creating new methods that deal with new data sources, maybe inventing new data sources, all leading to new knowledge. And the last one there, which is in the name of half of my job, is translation. How do we take what we generate in a research setting or an academic setting and translate it into the real world and make it useful to actually implement these changes in social goods? So here's my set of questions about data science for social good in academia. Like I mentioned, institutions talk about it a lot. They claim to value it, but there's few specifics in much of anything that I've seen, including my own institution. They don't tell me what to do at all. They give me very few guidelines, and then I'm expected to do it. So how should academics train and be involved in order to make a contribution in this area? Very important there, that second bullet point. How do we keep analytics honest, fair, and representative? So there's lots of discussion, especially in academic settings, about algorithms that are biased in one sense or another, or create unfairness. So what do we do? What's our responsibility in terms of minimizing that aspect of data science? Who else is involved in what we do, and how do we work effectively with them? A lot of this happens in industry, so we need to have an interface between industry and us. And then there's the people we hope to affect through data science, and we have to be able to interact with them. What is research in this context? How do we get academic credit for the work we do? The kind of credit that moves you toward tenure and promotion. Is it possible? Do you need to make proactive decisions to make sure that your institution views what you're doing in a way that can be credited to you. This point here, potentially lots of money involved. Different from a lot of the work that we do in academia, there really is potentially a lot of money involved in this. People in other parts of the universities do this kind of work, create startups, and then sell them for millions of dollars. Commercial enterprises do this kind of work or claim to do this kind of work and generate gigantic cash flows. So that raises a whole bunch of interesting questions about how you support this work. There's a lot of money out there. How do you orient yourself so that you're still being academic and you're still actually producing a social good, and balance the money interests involved? Foundations want to support this kind of work, and they do have a lot of money, and it's interesting dealing with them to figure out how to do that. And then I think the last bullet point is important to me. What is our responsibility in terms of the products we produce? And it's begun to become quite a big concern of mine because we're licensing software. How do you make sure that what you're doing is as honest and fair as possible, and then gets used in a way that's honest and fair, and doesn't actually create legal liabilities for you or the people who you've designed it for? And I have a very specific issue here in this talk I'm about to give you about verbal autopsy. We produce causes of death using a machine learning-esque kind of approach, using very, very, very limited data. So the result is very uncertain. And cause of death is very important on a death certificate, because some causes allow you to claim on life insurance policies and other things like that, and some don't. So in a setting where you're producing this kind of information primarily for a public health consumption, people are very tempted to use it in this other very strictly legal way. And until now, I think most people's answer to this question is, well, you let them sort it out. I'm beginning to think that we have to be much more involved in helping sort that out. Okay, so I have a lot of slides, so I'm going to carry on. I've put together a few points here that I want to come back to at the back of this talk and evaluate what we're doing in the context of these questions. So I'll just read them really quickly. Is the ultimate objective a consequential social good? I feel like a lot of social goods that get talked about in this context are being defined by computer scientists and engineers, and they're really methods in search of an application rather than a real application. So are you being honest about really producing something that's useful? So is the approach affecting inequality in a negative way? That's that whole algorithmic fairness business. Is the approach feasible in the target context? So you have some context where you want this work to be applied. Can it actually be applied reasonably in that context? Is it self-sustainable in that context? What are the potential unintended consequences, both positive and negative? I think we have to think through those. And if there are some negative ones, try to think through them and figure out, can they be remedied or resolved in some way as you move along? So is there a feasible, useful plan for the future? And primarily here for us to disengage at a certain point. If we've done a lot of research and created a useful tool for someone, how do we move that tool into application and then step back from it without disrupting the ability of whoever's using it to continue using it? And the last point is for us, is the overall approach to what we're doing academically sustainable? Is there training that we can provide for young people trying to move into this field? And once they've done that, is there a career path for them within academia that allows them to move forward? Okay, so how did I get to this point of doing this? So I was born in Kenya and I grew up in Tanzania and Kenya. And so I have put a great big Kenyan flag up there. And I've shown you where Kenya is on the map here. It's here. It is not down here. People look at me, they see I'm white. I'm South African. As soon as they hear I'm from Africa. I have colleagues who I've known for 30 years who still think I'm South African. I am Kenyan. I'm a Kenyan citizen. I'm an American citizen. Please try to keep Kenya in your mind. I don't want to be misclassified as South African. This happened in a meeting I was at last week at NIA. I was South African. So anyway, I moved to the US when I was 16. So I grew up in a developing world context. My dad was a veterinary officer for northern part of Tanzania, and then he turned into a development worker doing all kinds of things there. So I kind of saw all of that as I grew up. I went on to do an undergrad at Caltech. I did biology, mainly neurobiology and engineering, mainly computer science and electrical engineering. I did graduate work at Penn. I did a PhD in demography, and then I did Fulbright working in Zambia, doing a lot of data collection with anthropologists. So I got into this general sense of what I'm doing now through anthropology. Then I did a postdoc in South Africa. It was about 5 years, and I worked mostly with health and demographic surveillance system sites doing data collection and data management. And then I worked for about 10 years with a group of statisticians at the University of Washington, led by a guy named Adrian Lackery, who, if you are a statistician, you will know. If not, he's a very dynamic person who works on developing methods within sociology, epidemiology, demography, a bunch of areas. I learned a lot from him, and essentially through that experience decided that I wanted to try to put all of this together and do work with data methods aimed at solving problems where I come from, which is mostly Africa. Okay, so here's the social good that I'm interested in working on. So this map displays in colors from red through to this turquoisey, that's low to high, and white being no data. So red to turquoise, challenging to good. And the number, which is being categorized with that color scheme, is an index of vital statistics performance. And so this wraps up a number of things. The coverage of the system, how accurate it is, how many births it records, how many deaths it records, and how many of the deaths get a cause. And so what you see is we have the developed part of the world, high-income countries, North America, we have Western Europe, we have Australia, and a smattering of places elsewhere that are doing very, very well on this. So what that means is that all of these vital events are captured, they're captured accurately, and the deaths all get a cause. Then we have parts of the world in the middle where things could be going quite well, Brazil being a big example, South Africa being a big example, and so on. Then we have Africa, and you can see Africa is mostly white, and where it's not white, it's predominantly red. So we have a real gigantic problem throughout the whole continent of Africa, which is a big fraction of the whole world. So here are the interesting high-level takeaways. About 60% of deaths and causes are missing globally, and about 35% of births. So what I want to work on is the deaths and do what I can to improve the quality of this death reporting globally. Now, what I'm going to focus on is the cause part. Okay. So this is obviously important because it's a fundamental indicator of health. Just the fact of the death is a fundamental indicator of health. And beyond that, knowing what the cause is helps you categorize public health public health conditions by importance, and then you can do whatever you want to try to address them. So verbal autopsy, what I'm going to do now in the next few slides is run through quickly what it is, and then talk about what our team is doing to work on it. So here are the basics. It's a very old method. We have a publication there, Chandramohan et al. In 21, that kind of goes through the history in a nice way. But basically, since the 50s on, starting with people in anthropology, public health, epidemiology, what they did was try to design a method that would get a cause of death without all of the traditional infrastructure of autopsy, medical certification, and things like that don't exist in resource-constrained settings. So verbal autopsy is the only feasible method where those traditional high-income country systems do not work. And it's feasible because it's cheap. All you have to do is talk to people instead of having all of the infrastructure and highly trained individuals to do the rest of it. So it's very challenging in general. The interview is difficult. You're talking about recently deceased individuals with people who were close to them. The data are inherently noisy and contain comparatively little information. You're asking a person to recollect details about another person's history of illness and eventual death. Cause classification is very, very difficult. The problem is high dimensional, and you have very small amount of information. So from a methodological point of view, super challenging. Then like I just mentioned, the results are noisy and uncertain. They require careful interpretation. And although feasible, it's still very difficult to implement. So down here at the bottom, I summed it up I did this about 10 years ago. I was looking for something interesting and useful to do. And the main qualities of this are very consequential. We saw the map. Many potential users, again, the map. And there's lots to do. Very difficult method, lots of things that can be improved. So something to keep you busy for a long time. So here's the basic outline of exactly what it is. So we have a predefined set of causes, and they're not the typical causes. Those of you in epidemiology or public health familiar with the ICD coding system. These are groups of ICD codes that we feel verbal autopsy can speak to. Then we have important signs and symptoms. These are the VA indicators that are collected through our interview. And then we have something called symptom cause information that links the indicators to the causes. So this is another data source outside of those two that allows us to understand the relationship between the VA indicators and the cause list. We have then, to apply VA, we have a interview with the close caregivers of a recently dead person. There are hundreds of closed form questions, and then there is optionally a narrative account of death. So this is typically quite a long interview. It can stretch up to a couple hours and may include this piece where someone gives you some free-form text as to what happened. The data are used to classify the death into the VA cause list, and the result is two things: an individual level cause of death for that particular death, and a population level metric of the burden of disease. And what that is the count of the number of deaths in each category, so effectively the distribution of deaths by cause in that population. The second one is what we're interested in for epidemiology. The first one is obviously important for the family and the people close to the decedent, and possibly for the civil registration vital statistics system, and possibly maybe someday for legal purposes. So the VA instrument itself, there's two standards. There's a WHO global standard, which has its origins in the early 2000s. And then there's another group, the Population Health Metrics Research Consortium, that also developed a little bit later, a kind of a competing system. That one has two versions, a long and a short version. And then each instrument has kind of spawned its own ecosystem of data collection, coding mechanisms, and interpretation tools. We're going to focus on the WHO version. So the VA interview, what I'm going to do is just outline some of the challenges, and then in a minute, I'm going to tell you what we're doing about them. So the standard instrument is in ODK form. Those of you who do data collection may know about ODK, the Open Data Kit. It's a commonly used electronic data collection system. Since VA is conducted all over the world, these interviews happen in many different languages and sociocultural settings, which raises a lot of thorny issues with regard to the data generation process. Apart from the standard, a few standard training materials, not much is done to standardize the interview. So there's a wide variety of circumstances in which these interviews are conducted. Implementers always modify the instrument, so they add and subtract things, and they play with the ODK, which affects the data. The interview is long and complex and very emotionally challenging. Emotionally challenging for the person who's providing the information, and it turns out for the interviewers as well, having to listen to this, it's almost like being a counselor. You're listening to the whole thing, you're having to process it, sometimes you have to help the person get through it, and you have to do it repeatedly over the course of the day and then get up and do it again the next day. And obviously lots of different languages and potential cognitive frameworks used, and how does your instrument interact with all of those. So this is the second to last bullet point there. This interview itself, the way it unfurls for each death, is an important source of consequential variability in the data. And we have to understand what that is in order to conduct our analysis in a reasonable way. Okay, the VA data themselves, because they're complicated, they require systematic checking and kind of consistency verification. So we have a whole bunch of software that automates a set of data quality checks on these data and then transforms them. So the first form is the raw data coming from the field, and then the second form is a processed version of those data that is appropriate for putting into our automated cause coding algorithms. And that is, the process version is basically binary indicators and word counts from the narrative. So turning to what to do with the data now, how to make them useful. The traditional thing to do is something called physician-coded VA. So in this approach, you have a physician read the VA transcript. So they read the raw VA transcript and the narrative, if it exists. And then they simply tell you what they think the cause of death is. And sometimes they give you an underlying cause, an immediate cause, and a contributing cause. If you have two physicians read the same death, they very rarely agree. So this is a big problem. It means that that particular method is not replicable in any sense, and kind of non-standardizable. So what happens to address that is that there's a kind of consensus building process, and you have either 2 or 3 physicians read it, and they have to come to a consensus. But if you choose 3 other physicians, the consensus may differ. So this is really a big challenge. So just wrapping it up, comparatively specific causes, physicians are good at getting fairly low on the ICD tree, more accurate in general. But then the 3 at the bottom in a reddish color, non-replicable, inconsistent, and contextual, slow, costly, you have to pay physicians to do it, and often, of course, takes their time away from dealing with live patients. So this is not the way to do it in a large-scale setting like a CRDS system, where you want to be processing thousands of deaths. So the alternative is computer-coded verbal autopsy. And the idea is essentially replace a physician with a machine and do the best you can to classify the deaths into the VA cause list using an algorithm. So there are 3 components to this. This pointer doesn't work on this screen at all, so maybe I'll just go point at it. So you have the VA data themselves. You have the symptom cause information that relates the symptoms or the indicators to the causes, and then you have an algorithm logic. So the data, typically this binary coded deaths by symptoms matrix. You have an algorithm that combines it with a symptoms by cause matrix, usually decimal numbers, bunch of different ways you can combine those, and you produce this deaths by cause matrix down here. That is a set of also decimal numbers that rank the causes for each death. And typically you just take the cause with the highest metric value, whatever it is. That's the cause of death, and then you sum those up to get your cause-specific mortality fractions. So we're going to talk a little bit more about the algorithms in a minute. The benefits here, they're cheap and fast, completely replicable, unless you're using a sampled type algorithm, a Bayesian algorithm of some sort. But then if you do it again and again, have enough deaths, it's effectively replicable. Doesn't require physician time, can be fully automated. You can wrap this up into systems that you can then go let operate on their own. And it's comparable because you've completely standardized the way this logic works. Now that still leaves the data as a variable and the SCI as a variable. So not completely comparable until you've standardized the SCI as well. Now the downsides, comparatively less specific in terms of the ability to classify causes, less accurate in general, still challenges with being context specific because those SCI typically come from a context and then people apply them in different contexts, and performance. So some of the methods, namely the one we created, is very computationally intensive. So that's a quick overview of those. Then I want to talk just real quickly about the VA causes of death. These are at the individual level. They're in the VA cause list, so you can't combine them with other systems that are using ICD codes. Physicians often produce a more differentiated version, and algorithms produce these decimal valued metrics that you can use to rank. And most of those algorithms are effectively deterministic, and they also produce undetermined causes. And the undetermined causes are effectively causes that are hard, or deaths that are hard to classify. And the algorithm is producing metric values that are all very small. And the thinking is then if they don't reach a certain threshold, then we can't really be confident about assigning a cause, so we call it undetermined. Our algorithm in silico VA tries to address that particular thing and not have the undetermined cause and replace that with distributions so we can have very low probability cause with very high uncertainty. The VA burden of disease, this is the ultimate metric that we want for public health. That's the distribution of deaths by cause. It's a population level indicator. In this VA field, we call it a cause-specific mortality fraction, so CSMFs. And in most circumstances, they're generated just by adding up. Again, in silico is a exception to this. We produce the CSMFs in silico by doing an estimation that jointly estimates the individual level indicators and the population level indicators with uncertainty so that they're consistent with each other. That's why it's computationally intensive. So, moving along, my goals for this data science for social good portfolio of work that I had to think about for Ohio State University was to do essentially these things. So research, create and maintain global standards for VA. If you're going to work on this larger scale, you definitely have to have standards. Everybody has to at least nominally be trying to implement similar tools so that at the end of the day, you produce results that are comparable. I wanted to greatly improve the replicability and comparability of VA causes of death and burdens of disease. Improve the VA interview. This is turning out to be far, far more challenging than I had thought. And the reason that's important is because we need better data and data that are generated in a comparable way. What we did right at the beginning, little tiny sideline here, when we were working on the algorithms, we did everything in the simulation environment. So we simulated the deaths, we created the method, we tested the method on simulated deaths where we knew the answer. And we decided just for fun to simulate a little bit of noise in the data. And it turned out that a very small amount of noise completely kills our algorithms in the simulated environment. So that's why I began to be obsessed with the interview itself. Then, of course, improving the algorithms, that's what we like to do. So lots of work to work on algorithms themselves and on the general field in which these algorithms are created. And then moving on to creating software in a research context, software that simply performs the work that we describe in a paper. So put up an R package that accompanies a paper so that people can see exactly what we did. But then in a routine use setting, a completely different kind of software that does the same thing, but does it in a way that the users can interact easily with. So R is a no-go in the real world. You need GUIs and very easy to install things that work on Windows. A whole new challenge for us. And then last, create this reference death archive, an archive of deaths that have, well, I'll talk more about it in a minute, but an archive of deaths that we can use to generate the symptom cause information and essentially train our algorithms. And then on the implementation side, completely separate from research, create methods and software to integrate all of this into large-scale mortality surveillance systems like CRBS, support the rollout of that, so the training and so on, and then support the continuous reporting of the various results in a context that policymakers and decision makers can use. So here's our team. So I just want to run through real quickly and make you know that there are a lot of people involved. So over here is the kind of core team that we have. And I'll just point out the long-serving members. So Tyler McCormick and I started doing all of this about 10 years ago. Richard Lee was a graduate student with us in statistics at that point, and he's gone on to be an assistant professor at Santa Cruz. And Jin Wu is a professor at Michigan in biostats. And that's kind of the core of our old algorithm development team. Then we have my wife, Clarissa, who is a linguist, and she works with Nicole Angotti, and they're beginning to make some progress on understanding the interview and helping us understand how to improve it. And we have a variety of graduate students. UHU right now is doing a lot of work on this with us. We have countries that are implementing our methods. So we have Rwanda, Ethiopia, Tanzania, Zambia, Solomon Islands. We do work in Kenya and South Africa and a few other places. And there's a bunch more here that are waiting to use these methods as soon as we have them up and running. Cobus Herbst at the Africa Health Research Institute in South Africa is helping design this reference death archive that we will put at the WHO. This individual goes by the name Burns because he is remarkably similar to Burns from Simpsons in his look. That's not my nickname for him. That's what he asked me to call him. So he's at the pathology department at the University of Sao Paulo, and his group will be producing a bunch of the reference tests that go into our archive. And then finally, we have the WHO verbal autopsy reference group, who I'm a member there, and we support them in a whole bunch of ways, developing and maintaining the standards. So that's our team. And if you see these slides later on, there's a link there to our website. So here's what the team does in kind of diagrammatic form. We start with the WHO and the standards. And everything we do is to help develop those standards and move them in the right direction. That is a consensus process. It's very slow, and a lot of people are involved. We're just one little piece there. We try to orient the rest of our work so that it fits with these standards. So we spend a lot of time working on software, specifically the creation of the algorithms, testing, and so on. So that's basically statistics, and we publish that in statistics journals. As part of that work, we're obviously very concerned with the data, what they look like, their characteristics. Those come from the interview, and the interview is organized by this standard instrument. So we're spending time there too. Then the software is used and integrated into large systems. So we figure out how to do that. And we're kind of serving two audiences, the research audience and the routine use implementation audience. The VAs happen in those two categories as well. The data comes back to us, both as a traditional research thing where we actually produce results and analyze them and publish them, but also we do a lot of work for people, basically contracts essentially, where we analyze things and just give it back to them. And we don't ship it. Then they will be coming very soon into this reference step archive. And the reference step archive will be producing symptom cause information that comes back to our software. And I'll talk a little bit more about that in a moment. Of course, software produces the causes of death and disease. And then we have all those implementation partners, those countries and NGOs that organize that work, who we work with very closely. So here's exactly what we're doing. So we have the interview. The objective is to standardize it to the extent possible. This is, cannot standardize an interview across all of the sociocultural settings where it's happening, but we want to do as much as we can. And that's going to improve the data quality. So I think I've covered most of that so far. Here, in terms of VA cause assignment algorithms, this is our remit. We face a extremely fractious literature here, some very disingenuous publishing, publishing that it very much appears to purposely obfuscate exactly what's happening. So in order to get to the bottom of that, we had to replicate everybody's paper and try and figure out exactly what they were doing, because what they described they were doing didn't make sense when we actually tried to think through it. There were some very inbuilt rivalries, very difficult. Everything was hidden, proprietary, non-reproducible. So we replicated and reverse engineered everybody else's work and open sourced all of it to change the kind of the dialogue in this little subfield. And it worked. It was very unpleasant, but it worked. People attacked us. People threatened to sue us. Yeah, it was interesting. And then people threatened to sue us, but told us they would sell us a look at their code if we wanted to give them $100,000, which we said no. Our objective there is open source everything and then do all of our work in an open source way. Create a standard framework for running all of these algorithms so that a data person who wants to analyze their data brings it into our software. They can do our thing or they can do our competitors' thing. And they can do it kind of on a fair basis, and then compare the results if they want. We created a new algorithm, this in silico VA. We want to work to improve the symptom cause information for all the algorithms and then work on a completely next generation version of the algorithms. In terms of the software, like I just mentioned, we want to maintain a commitment to open source. That's what we call ourselves, openVA. That was in direct response to the very closed nature of this subfield. So all of our theoretical work comes with open working code. So we have R packages If you do a Google search for CRAN and verbal autopsy, you'll find a bunch of our packages there. And we have a GitHub site with everything as well. In terms of global standards, our approach is to work super carefully and consistently with WHO, maintain a membership in that advisory group, focus on maintaining the standards. We work a lot on this ODK data collection system, which is frustrating. And then that group produces training materials, question by question guidance for interviewers, not very effective or very good, but it does it, and a wide variety of other things. They have a web page that you can go look at. So this is interesting. Students sometimes ask me how you get involved with these kinds of things, and I'll come to that at the end of the talk. Now, the reference death archive, a little bit more about this. So the algorithms themselves, like I just showed you in cartoon form, combine the data with the simple cause information and wind up with a classification of deaths. The SCI describe the relationships between the VA indicators and the VA causes, and effectively they drive all of the algorithms. We did a little piece of work where we tried to decompose the whole process and look at the effect of variation in the SCI, variation in the data, that's obvious, and variation in the algorithm logic. The SCI accounted for the vast majority of the total variation. So they're very, very important. And for the algorithms to be accurate and comparable, the SCI need to reflect a wide variety of epidemiological circumstances, and they need to be updated through time because epidemiological circumstances change. HIV came along, then HIV treatment came along, and COVID came along. So you can't just have a static set of SCI for running these algorithms. So there's two approaches to creating them. One is to crowdsource the SCI from physicians, and that is done by defining the conditional probability of each symptom given a cause, assuming conditional independence given cause. And the other approach is to calculate a similar number directly from reference deaths that have both a standard verbal autopsy and a trustworthy cause from an independent source. So the crowdsourcing SCI is comparatively low information compared to the empirical version. But because of the dimensionality of this whole issue, the empirical SCI is very difficult. You need tens of thousands, maybe hundreds of thousands of reference deaths, and you need those reference deaths from all over the place. And you need to be sure that you have enough observations in each cell, deaths are not distributed evenly by cause, et cetera, et cetera. So you need a lot. And that's very challenging. So the idea is to put together an archive, host it at a trusted third party like the WHO so that everybody has access. Researchers can create and improve SCI, develop algorithms, test and validate them using those reference deaths that everybody has access to. So we can develop ours and test it on those deaths. Somebody else can do the same thing and do a valid comparison because they are using the same framework for doing the comparison. And then users also primarily will benefit from this by having continuously updated SCI with an appropriate, hopefully, coverage of epidemiological circumstances and available in a way that can be programmed. So having an API that gives you access to all of this. So what have we accomplished in all of these categories so far? So for the interview, I have to say, very much a work in progress. This is super difficult. What we've done is observe the interviews in a lot of different contexts, and we have verified our intuition that things are happening very differently in different settings. So it is a very big and important potential source of variation. We've kind of characterized that. We've understood that the interview designs are very different with consequential differences. For instance, some interviews are done in a group setting where you have input from a whole bunch of people. Some are done completely in private and only have access to one individual. Some can deal with the delicate topics, HIV, for instance, sexual violence, without any trouble. And in other settings, you can't talk about these things at all. Language use, highly variable. Translation and interpretation standards, also highly variable. So I hope you're beginning to understand that If this step doesn't happen reasonably well, then everything that comes afterward is pretty much a hopeless endeavor. So we've essentially gotten to the point where we have a fairly good understanding of the challenges, and we're beginning to work on thinking through how to remediate those. In terms of the algorithms, this is where we've spent probably the most effort. We've invented in silico VA. It attempts to address the undetermineds, get rid of them, replace everything with a true probabilistic framework that keeps the individual and population levels consistent with each other, and produces distributions as outputs for everything so that we can apply a traditional way of thinking about uncertainty, precision, confidence, whatever you want to call it. We re-implemented everybody else's, as I mentioned, and then we are working on new algorithms. One of them was accepted yesterday in the Annals of Applied Statistics. These new algorithms attempt to characterize dependence among symptoms and give us the ability to deal with multiple domains at the same time. So you can imagine deaths coming from, a part of Africa where malaria is a big issue, and then a different part where HIV is a big issue, using SCI that is able to differentiate those contexts and wrap it all into a single algorithm that handles things like that. Then we, I think we did the only fair comparison where we decomposed everything and looked at all aspects of variation that could go into creating different results. And we evaluated everybody's algorithm, and we came to the conclusion that none of the algorithms work particularly well. SCI is the most important feature so far, and that ours works a little bit better in most settings, but not all settings. So we were hoping for something much better there, but well, we still have lots to do. The last bullet point there, a new thing we're doing is looking at how to use additional information in the SCI. So the reference desk can have the VA and a reference cause, and then other information that helps you potentially classify that death. We want to generate SCI using our training data from those deaths that incorporate the extra information, and then use it in the algorithm on deaths that don't have the extra information. So what we're using is minimally invasive tissue samples for that right now. Software, we have done a lot of work here. We have the openVA suite of algorithms in R and Python. We have something called the openVA pipeline, which integrates all of this into a CRBS workflow in a lot of countries in Africa and Asia, parts of Latin America. In a nutshell, what it does is automatically retrieve the deaths from ODK, automatically process them through any of the algorithms. User can specify what they want to do, automatically wrap up everything, including the raw data and all of the results, into a little package that then gets uploaded automatically to something called the District Health Information System #2, which is an open source health management system that a lot of these countries are using. We have a piece of software in R and Python that does all of these data checks and transformations. We deliver it in a whole bunch of different ways. We have packages, Docker images, executables. We have a paper, openVA toolkit in the R journal, which is kind of a companion, a big companion to the whole suite of software that walks you through how to use it. And then we recently developed an open source GUI-driven Python version of everything by listening to our users. And they said, all of this fancy stuff is cool, but we don't want it. We want something we can click through and just do simple analysis. So that's what we made for them. And we had a workshop last month in Dar es Salaam where we rolled it out. Thank God it worked. And they were so, it was so interesting. Normally I do these workshops and installing everything on everybody's computer is a big pain, and Java gives you a pain, and R gives you a pain, and everybody has different configurations. This stuff installed perfectly, and before I even got to the end of my little intro, I had people playing with results. So, and this is not our approach. We were asked to do this. In fact, we were paid to do it, and we did it begrudgingly because it's a lot of work to write new stuff and learn how to do GUIs, but it worked out really well. The Reference Death Archive is a new project. The Gates Foundation gave us money to get going on it. The deaths will have a WHO standard VA independent cause, a bunch of different sources for that independent cause, and many of them will have this minimally invasive tissue sample information. which is a variety of tissue samples that can be taken from a recently deceased corpse using large bore needles. So you don't have to do all of the cutting and reconstruction that many cultures don't want you to do. And in some cases, you can just take samples of different tissues that are and fluids that are easy to access. You can do a whole bunch of things that are very helpful in terms of understanding how that individual died. We're building the computational infrastructure for that to be hosted by WHO in Geneva. And the reference deaths are coming from the CHAMPS and COMSA projects, mortality surveillance projects supported by Gates, that some of you might be aware of. CHAMPS is for children, COMSA is for everybody. And the Brazilian vital statistics system is absolutely beautiful. If any of you want to do work like this, go to Brazil. What they do is have a traditional autopsy on all of the deaths that need it, medical certification for the rest, very few that don't get that attention. And they have worked out all of the pathology in a way that's actually feasible in a lower resource setting like Brazil. So it turns out these are the magic people for developing this kind of method and moving it into African settings. Okay. Some limitations of our work. There's a very long list here. I'm going to skip through it because I'm running out of time. But you can note right at the bottom, I've got ... Lots and lots and lots of challenges and things that didn't work particularly well the first time we tried, or if it's taking a lot longer than we wanted to. So back to this slide that I presented in the beginning. How are we doing on the data science and social good guidelines? Is the ultimate objective a consequential social good? I think yes on that. Is the approach affecting inequality in a negative way? And I'm going to say maybe, very firm maybe. And that's because of the SCI. We have SCI right now in two forms, neither of which are good for everybody and definitely disadvantage certain populations. So that's why we're beginning to put this huge push into the SCI and the reference death archive so that we can generate training data that make the whole enterprise more fair and more useful for everybody. Is it feasible in the target context? Yes, fairly. Self-sustaining, probably. The national governments that we're beginning to work with are very interested in this. They're spending some of their own money, getting their feet in the water, and things are going well, and I believe that they will probably be willing to invest in it. At the moment, it's the Bloomberg philanthropies that are paying for most of that work. What are potential unintended consequences? There are many. Uncertain causes used inappropriately or with too much confidence. I sketched that little legal dilemma at the beginning. That's the main one, and it's a very, very big one, but there's more. Can negative unintended consequences be resolved? I'm an optimist here, and I put probably. I have colleagues who are definitely disagreeing with me and would say no, that we need to be very careful and we need to basically stop doing this in some settings. I believe that a little bit of noisy information is a hell of a lot better than zero information at all, especially for something as important as this. And I think the legal issues can be solved. Legal systems are human creations, and we can simply work on it. Is there a feasible, useful plan for the future? Yes, getting there. If academics need to be continuously involved, how is this supported? I think we can deal with that. And I think there's ways of having academics move through their careers and get promoted, or at least I've managed to do it doing this kind of work. So I hope others can too. I'll skip future works. And I'm going to skip that and go right to here. So how do you prepare for this kind of work? I think some of you may be interested in this. I think the first and absolutely most important thing to do is that question. You have to have something that's actually worth doing and worth doing for a long time. So spend some time thinking through that and prioritize problems that are very difficult and other people have kind of given up on. Don't take that as a signal that they can't be worked on. They can be worked on. And that means that you'll have something to do for a long time. I think you need training in a bunch of things. Computer science, if you're going to do data science, is very important. Statistics is critical, absolutely essential. And then a substantive field, sociology, demography, epidemiology, whatever. Then this other one is something that I really wish somebody had told me earlier in my career. These kind of projects become big. There's a lot of money. There's a lot of people. these are mine, or at least happening internationally all over the place. I really needed basically an MBA or something that taught me some skills for how to manage a lot of money, a lot of people, a lot of very complicated activities, because that's basically what I do now. Work to develop a very diverse network of colleagues. Those are the people who are going to help you through it all. Same thing with funders. Don't go just for the traditional funders. If you can possibly work a way to be supported by non-traditional kinds of funders, take advantage of those things and do that. And the last two, you're going to have to accept slower progression to your career. You're trying to do more things that are more complicated than a straight up, going through a sociology career. And you're going to have lots of people that tell you that this is not a good thing to do. My PhD advisor told me everything that I'm doing now. He told me that was a career killer. Ciao, goodbye. I'm done with you. And many other senior colleagues did as well along the course of my career. But it did eventually work out.